Hey, welcome back to Calculus. We're going to finish up section 7.4, partial fraction decomposition, by looking at kind of two remaining cases. We've already dealt with the case where we have distinct linear factors or repeated linear factors in the denominator. So now what we have to deal with is we have irreducible quadratic factors in the denominator. So a polynomial is irreducible if you can't factor it anymore. Every polynomial with real coefficients can be factored into either linear or irreducible quadratics. So this is kind of our remaining case. Okay, so we'll look at that case and we'll get some more practice with this method of comparing coefficients. Okay, so how do you know when a quadratic polynomial is irreducible? Quadratic polynomial, you remember, looks like ax squared plus bx plus c for numbers a, b, and c. A is not zero. It's irreducible when the thing that would be under the square root in the quadratic formula is negative. Yeah, so if your b squared minus 4ac is negative, that polynomial can't factor anymore. So if you have such a thing in your denominator, you have to put in two unknown constants. You have to put in a term in the partial fraction expansion that looks like ax plus b over your irreducible quadratic. All right, let's look at this example down here to kind of illustrate what I mean. So here I've got a rational function. I've already factored its denominator to get us going here. So I've got a linear factor. So we treated that last time. We'll have to treat it the same here. And then I've got this quadratic factor, x squared plus 1. And I'll leave it to you to check that if you compute out it's b squared minus 4ac, you're going to get negative 4. So that's an irreducible quadratic factor. So from our linear factor, the x plus 1 from last time, I need to put in an unknown number, just one of them, because that linear factor is to the first power. And then for this quadratic factor, sorry about that, for this quadratic factor, I have to put in two unknown numbers. I've already used the letter a, so I'm just going to continue down the alphabet and put in a bx plus c, and that's what I have to account for that irreducible quadratic factor. So up here in the formula, they wrote a and b. I'm using b and c because I already used the letter a. Okay, so for an irreducible quadratic factor, two unknown numbers. And then for a minute, we proceed as usual. We clear the fractions. So multiply both sides of that equation by the denominator. When you multiply the a term by that denominator, the x plus 1s will cancel. So you'll be left with a times ax squared plus 1, the quantity. When you multiply the second term by that denominator, x plus 1 squared cancels, so you're left with bx plus c times x plus 1. All right, and then I'm going to illustrate the method of comparing coefficients. I'm just going to multiply this out. So that's ax squared plus a. Multiply out that side, you get a bx squared plus cx plus bx plus c. And then just gather your coefficients. So the coefficients of the x squared term is a plus b. The linear term's coefficient looks like it's c plus b. And the constant term looks like it's a plus c. All right. And if I compare those over here on my left-hand side, I've got no x squareds plus 1x plus no constants. So I'm just going to compare those coefficients, right? A plus b has to be 0 because there's no x squareds. C plus b has to be 1. A plus c, excuse me, has to be 0. So I'm just going to write that down. My system of equations here. Let me actually left justify it a little bit more so I have some more room to work. So a plus b has to be 0, the coefficient of x squared. C plus b has to be a 1, and a plus c has to be 0. All right, so how to solve such a system? Well, you can do it any way you like. It's basically the idea is you isolate and substitute. When I look at this system, the first equation tells me that b is the opposite of a, and the third equation rather tells me that c is also the opposite of a. So that tells me that c and b are the same. That's personally how I look at it. And if c and b are the same, then this middle equation says that 2 times one of them, say b, is equal to 1. So then I find out that b is a half. Well, then that means that c is a half. Remember, because b and c are the same, a is the opposite of b or c. So a here is minus 1/2. Okay, so that's one way to solve that. It's not the only way to solve that system. So let me just kind of return back up. Where am I going to put those a, b's, and c's? Remember, we just found that b and c were a half, a was a minus a half, right? So I need to replace those values right there. So if I do that, maybe while we're looking at it here, I'm going to write the A was minus 1/2. So that's going to be minus 1/2 times the quantity 1 over x plus 1. And then since B and C were both a half, I can factor that out. So that's going to be a half times x plus 1 over x squared plus 1. All right. So when we go to compute our integral, maybe the best thing I can do is just scroll up here. This is the form that I'm going to be integrating. The integral of my original problem, I'm going to write, well, it's the integral of this right-hand side, which we're just going to split up. We're going to split up. So let me make a copy of this and drag it down. You can pause and think about what I'm saying. Got some room to work down here. So we're going to integrate this thing with respect to x. And in order to do that, I'm just going to split it up. I'm going to write that this is minus 1/2 the integral of 1 over x plus 1. That's going to give us a logarithm, plus 1/2 the integral of x plus 1 over x squared plus 1. Okay, and that integral, before I start integrating here, I hope I have left myself enough room. I'm going to split that thing one more time. So I've got 1/2. Now, how am I splitting it? I'm going to write this as x over x squared plus 1. Plus 1/2 the integral of 1 over x squared plus 1. Okay, I'm just distributing my denominator. So now I've got this thing written out in a form that I can perform the integrations. I'm going to be a little bit brief here in this. You can ask me about it in an office hour if you need some details here, but if we keep drilling down too far, these videos get too long. So the integral of 1 over x plus 1 is a logarithm. The logarithm of x plus 1, an absolute value. This guy, I would do with a substitution. Yeah, I would let, here, I can write it here. I would let u equal x squared plus 1. So du is 2x dx. So that integral has the form 1 over u du up to a constant. So I'll let you work out the details there, but that constant would be 1/2, so it'll come out, and then you're ending up getting a natural log of x squared plus 1 when you do the integral. All right. And then what about this one down here? The antiderivative of 1 over x squared plus 1, I'm going to do that by the just know it method. That's the arctan. The inverse tangent's antiderivative is x squared plus 1. Done integrating, so I'll add my constant, and then you can just clean this up a little bit by rewriting your constants. So I'll leave it to you to check that if you carefully take the derivative of this expression and simplify it, you should get our original rational function. All right, so when you have an irreducible quadratic factor, you have to put in some more constants. And it's not going to be uncommon for the inverse tangent to appear in some of the answers, because you're going to get things like this 1 over a square plus a square. Nice. Okay, so I'm just going to do one more example with you here that kind of illustrates what to do, because these things, you just have to practice them. There's no number of examples that I can do that's going to get you to be proficient in this. If you want to be proficient in this, then you have to put in the time yourself. There is one more case we haven't talked about. It tends to be a little bit computationally intensive, but the question is, well, what about when you have an irreducible quadratic factor that occurs to a multiplicity of bigger than 1? It's just like the linear case. You have to put in unknown constants for every power of that multiplicity up to the one you have. So here it's written small on your screen probably. That's an r. The exponent is an r. So you have to build that irreducible quadratic. You're pumping up the exponent one at a time until you get to the r. So basically for lots of unknown constants. So this one, this last example that I'm going to do, I've written it out. It's mainly the illustration is to, the purpose of doing this example really is to, well, illustrate this fact, kind of show you by virtue an example that these computations get quite complicated, and the secret to doing this stuff is staying organized. Yeah, there's no shortcut to answering these kinds of questions. It's an algebraically intensive exercise, and when you're doing something algebraically intensive, the best thing you can do is to write many small steps and stay organized. Keep checking yourself as you go. Okay, so my example is that I would like to find an antiderivative for this rational function. You can see its parts. I've got an irreducible linear I've got a linear factor downstairs, so we know how to treat that. And then I've got an irreducible quadratic. X squared plus 4 doesn't factor. It's b squared minus 4ac is less than 0. But that irreducible quadratic is to a multiplicity that's bigger than 1. I chose 2, and I think that you'll see that it's going to make it sufficiently complicated. So what am I doing? I'm taking my rational function, my original thing that I'm integrating, and I'm writing out the partial fraction form. So what do I have here? Well, I've got an unknown constant for my linear factor, x minus 1. I'm calling it a. And then because this is a 2, I have to build in 2. I'm just going to use the alphabet. Bx plus c over that thing to the first power, dx plus e over that thing to the second power. If this were a 3, I'd need 2 more constants, fx plus g, I guess and then it would be x plus 4 cubed. So that's what that slide above was all about. So we have to find these 1, 2, 3, 4, 5 numbers. Okay, so how do you do that? You clear the fractions. So that's my first line here is I just multiplied both sides by the denominator of the left-hand side. I'll let you stop the video. Stop the video a lot here and check all of these computations. But here I've cleared the fractions. So I multiplied both sides by the denominator of the left-hand side. And then I skipped the details here. I did this on some scratch paper and I wrote it, but I gathered my like terms. So I multiplied out and gathered terms. Multiply out and gather like terms. And you'll get this. You get a plus b, that's the coefficient of x to the 4th, c minus bx cubed, and so on. Okay, so I'm getting my coefficients of x to the 4th, cubed, squared, 1, and the constant term. Over here on this side, I see that the coefficient of x squared is a 1, and the other powers of x all have coefficient 0, right? So I'm just going to take those coefficients and write down the system of equations, right? The coefficient of a plus b of x to the 4th is a plus b. Well, a plus b has to be 0 then, because there's no x to the 4th on this side of the equation. And so on. The coefficient of x cubed has to be 0. The coefficient of x squared has to be 1, because that's the one term that we have over there. The coefficient of x has to be 0, and the constant term has to be 0. Okay? So just like in the method before, I'm skipping a lot of steps here. This is a system of 5 equations and 5 unknowns. You have to do a lot of substitution. Maybe you'd start off by doing things like, I don't know, you can substitute. So this equation says that C and B are the same. So everywhere you see a B, you can replace a C. Could go for it like that. Maybe you like to do things like add these 2 equations together and B gets eliminated. So you get that A is equal to the opposite of C. If you added these 2 equations together, the e's and the c's would eliminate, and so on and so on. So it's not my business here to go into that. That's a skill that you've developed in previous math classes. Here I've just got the answers. Okay, you solve that system of equations, you get that a, b, c, d, and e are those 5 constants. All right, so I solved them. You can check my work. It's probably 10, 15 minutes worth of careful computation to find those things. Cool, but let's just move on. We have them. So what am I going to do then? I'm going back to my expression that we were decomposing, and I'm just putting in those numbers, right? So I'm putting in, say, 1/25th for A right there. But I'm going to write it as 1/25th times 1 over 1 minus, or sorry, x minus 1. And so on. If B and C are equal, minus 1/25th, then I can factor that minus 1/25th out, and so I would have x plus 1 over x squared plus 4. And likewise, D and E were both 4/5. I factored the 4/5 out. That's my expression. So when I go to integrate this thing, which is my intention, I'm going to integrate each one of these separately. Okay, and you can see I've got a little color coding scheme here because this problem is getting very long. So the first thing I'm going to do is calculate this first part. What is the integral of 1 over x minus 1? Okay, so let me let you see that still. Well, the integral of 1 over x minus 1 is a logarithm. I'm not adding constants here. I'll do it once at the end. So this blue part, it's going to contribute log of x minus 1. How about the red one? Okay, well, just like we did above, I'm going to split this fraction. Take the x over x squared plus 1, split it the 1 over x squared, or sorry, x squared plus 4. Okay, so I'm splitting that up. Uh, uh, this first integral, we know how to treat it. It's going to be with a u substitution. The second one, I'm just kind of giving you some hints of how I do this. This x squared plus 4, you could do a trigonometric substitution here, but I'm going to do this. I factored out a 4 out of the denominator, so I rewrote that denominator down there as x squared plus 4 plus 1, or x over 2 quantity squared plus 1. And then the reason I like that is because if I do a u substitution, here, the u substitution would be u is equal to x squared plus 4. Over here, I'd let u equal x over 2. Okay, so stop the video and make sure that you can recover these things. But when you do that, you're going to get 1/2 the logarithm of x squared plus 4 for the first antiderivative. You have a 1/4 out here. The second one would be 2 times the arctangent of x over 2. All right, so those are both u substitution integrals. So that I've got that's what I'm going to replace this red underlined expression, the integral of it. We've just calculated it out. It's this thing. Okay, you guys still with me? I need to do the green one. The green one, integral of x plus 1 over x squared plus 4 quantity squared. So how are we going to handle that? Well, similar to the previous one, we split the numerator. So we write it as 2 integrals. This first one is a straightforward substitution. You let u equal x squared plus 4. Du is 2x dx. So that'll just be 1 over u to the 1, the antiderivative of 1 over u squared. So I wrote out what that antiderivative is. And the second one, you have to use trig sub. Yeah, trig substitution is how I would do that integral. So I wrote out the details here. You can stop the video and kind of look along. I mean, listening to me do this at this speed, I think is absolutely worthless. So if I were sitting here watching this video, I would say, okay, well, he said do trig sub. So I'd stop the video and stop listening to my obnoxious voice and try to work it out and then come back and see if you got the same thing I did. If you want to see my work here, the trig substitution that I'm doing for it is letting x equal 2 times the tangent. Okay, so I worked out what x squared plus 4 is and what my dx is, rewrite that integral, and it all boils down to the integral of cosine squared, right? You handle that with an identity like in section 7.2, so I just wrote the antiderivative here. That's all in terms of theta, so I have to use my triangle. Again, I'm going too fast for anybody to watch this. You should be doing it yourself and then looking back and seeing if you get the same thing. Rewriting that in terms of sine and cosine and using my triangle, there's my antiderivative for that second integral. All right, and I've been scrolling all over the place. Now it's time to put it all together. Putting it all together, the original problem, we looked at a lot of partial fraction decomposition, and then this came from that integral above that I was underlining in blue. All right, it had a coefficient of 1/25, so I put it there. And then this was the red one. It had 2 terms. It had a coefficient of minus 1/25, so I put it there. And then this was the green one. Yeah, and in particular, that green one, we had to do a trig sub, which I was writing in this pink color up there. All the integration is finally done. So then I add my constant of integration. And whew, that was quite a little bit of computation. All right, so I hope that was useful for you to have that as you're moving along. Thanks for listening.